Okay, in this chapter, chapter number 10, rates of reactions. Now, reaction rates for everyday processes can vary greatly in their time. A banana may only ripen in a few days, a piece of silver may tarnish within a few months, and while a person ages over the course of many years and many decades. So there are various factors that impact the rate of reaction, and we'll focus on those for the learning goal for this chapter. We'll discuss how temperature and concentration and catalyst all can affect the rate of a reaction. Molecules that are reacting to one another must collide, and they must be oriented in the proper way, and also have enough minimum energy present in order for them to react to one another and form a product. That's what these graphics are showing you. So for this example, nitrogen and oxygen must be oriented this way in order to form the product of nitrogen monoxide. If they hit each other and don't have enough energy, then nothing happens. They just bounce off one another. If they bump into each other but they're not facing the right way, nothing happens. They bounce off one another. Same thing here. If they hit each other but aren't facing the right way or aren't oriented in the correct way, then nothing will happen. Now, even if a collision does happen in the correct orientation, there still has to be enough energy there to help break the bonds and to help the reaction complete and to form a product. So there are three conditions that are needed for any reaction to occur. The molecules must have a collision, first of all. They must be oriented in the correct way, and there has to be a sufficient level of energy for the product to be formed. And that level of energy is called the activation energy. It is the minimum amount of energy needed to break bonds between atoms of the reactants and to therefore form products. These two reactants, nitrogen and oxygen, oriented in the proper way, the energy is sufficient enough, this activation energy, then you will get the products. If this is too low, then nothing happens. Now, the speed of a reaction or the rate of a reaction is determined by either the amount of reactants that are used over a certain amount of time or by the amount of products that are formed over a certain amount of time. So here's a mathematical way to write this. The rate of reaction is equal to either the change in concentration of a reactant or a product over a set amount of time. There are various factors that can impact the rate of a reaction. Reactions that have lower activation energies will go faster than reactions that need higher activation energies, which just logically makes sense. If you don't need as much energy to complete a process, then it will happen much faster. For any reaction, three main factors that can affect its overall rate: a change in temperature, a change in reaction concentration, and also by adding a catalyst. And the first one we'll talk about is temperature and how it has a role with the rate of reaction. At higher temperatures, the reactant molecules will be hitting each other more frequently because they're moving much faster. So if you have particles moving faster, they're going to hit each other harder and with more energy. An increase in temperature will cause a reaction to happen faster because you have an increased kinetic energy. And for every 10 degrees Celsius of increase of temperature that you have, the reaction rate will approximately double. Another factor that can impact the rate of reaction is the concentration of reactants. If you have more reactants present, more reactant molecules present, the higher the possibility that they will collide with one another and make the reaction happen faster. If you have, say, just one blue ball and one red ball, not much possibility for reaction. But if you have two hitting with one, you have more possibility here. If you have two here and two here, you have much more possibilities for collisions. So the more reactants you have present, or the higher the concentration of the reactants, the faster the rate of the reaction will go. Another factor that can impact the reaction speed is something called a catalyst. A catalyst is something that will speed up a reaction, and it does so by lowering the activation energy. And like we talked about before, if something only needs a lesser amount of energy to happen, it will happen much faster. The good things about a catalyst are a catalyst is never consumed in a reaction. It's always going to be there, and it doesn't get changed. So it's there to be used over and over and over again. By lowering the activation energy, increasing the rate of speed for that reaction. All right, next we'll move on to chemical equilibrium. Now, in most chemical reactions, reactants are not completely converted to products because a reverse reaction can take place in which the products collide to form reactants. This is called a reversible reaction, and it's indicated by these double arrows. If a reaction is going this way, it's called a forward reaction. If it goes from here back this way, it's called a reverse reaction. These reactants combine together to form this product. This will break down to form these, and it goes back and forth, forward and backward, forward and backward. So when a reaction will proceed both in the forward and backward direction, it's called reversible. As these reactants collide, hydrogen and iodine, the forward reaction will complete. So what you're really getting with a reversible reaction is a synthesis reaction going forward, and then a decomposition reaction going backwards. And it goes back and forth, back and forth. Now, as the reaction progresses, the rate of the forward reaction will get slower and slower and slower, and then the rate of the reverse reaction will increase. And then when you're at an equilibrium, the rates of both forward and reverse reactions are equal. Neither direction is faster or slower than the other. They're both at an equal rate. That's what's happening here. When you progress with the reaction, the forward direction will get a little bit slower, and the backward direction gets a little bit faster until they meet at an equilibrium. Equilibrium is reached when there are no further changes in the reactant or product concentration. For this chart, it has the progress of reaction over here versus the concentration. So reactants will get a little bit less and less in the very beginning, and the products will get higher and higher in the very beginning. And then they get to a point where they're at an equal level, an equilibrium. All right, next we'll talk about equilibrium constants. Equilibrium constant for a reversible chemical reaction multiplies the concentrations of the products together and then divides that total by the concentrations of the reactants multiplied by each other. And this is a generic way how it's written: A, B, double arrows, C, and D. In this generic form, C and D are the products, and then A and B are the reactants. And this is the way that you would write this mathematically and how you would solve problems when it comes to this. The equilibrium constant is represented by K and then lower subscript C. So constant, the K for equilibrium. The concentration of this product raised to the power of the coefficient in a balanced equation. That concentration multiplied by concentration of the other product raised to that power. All that divided by the concentration of the reactant A raised to the power of its coefficient multiplied by the concentration of reactant for B. A general way to think about this is the concentration of the products divided by the concentration of the reactants. That's using a generic letters to represent the products and reactants. Here's one using a real formula, and then on the next slide we'll get into real numerical values. So for our reaction we've talked about, H2, hydrogen, plus iodine will yield 2HI. If you're finding the equilibrium constant using this equation, the concentration of the product, the main product here, raised to the power of its coefficient, 2, because there are 2 of these. And you can think of this as the concentration of HI multiplied by the concentration of another HI, that's why it's HI squared, divided by the concentration of this reactant, and it has no coefficient, so it's raised to the first power. That concentration multiplied by the concentration of the second reactant, raised to its coefficient. That's how you would write it. And now here's how you would solve it with real numerical values. Say for the equation we just looked at, the concentration of hydrogen is 0.10 molar, the concentration of iodine is 0.20 molar, and the concentration of HI is 1.04 molar. So now you're just plugging in the values for the equation that we just wrote. Over here it was a concentration of HI squared, so this value squared, all that divided by concentration of hydrogen, 0.10 molar, multiplied by the concentration of iodine, the other reactant, 0.20 molar. You do all this math and you get the value of 54. So a reaction at any specific temperature can only have one value for the equilibrium constant. The temperature does not change equilibrium constant. It may change the rate of the reaction, but temperature does not impact the equilibrium constant. Alright, given another reaction here, 2SO2 gas plus oxygen gas will give you 2 moles of SO3. For this reaction, your result is a higher amount of product here than there was in the first experiment that we just saw. So this high amount of product will give you a very large value for the equilibrium constant. So the values of Kc can be either really big or really small. It just depends on if equilibrium is reached with more products than reactants or more reactants than products. The size of that equilibrium constant doesn't change how fast the equilibrium was reached. It's just a comparison of the concentrations of reactants versus products. Alright, that experiment we just looked at had a value of Kc that was high. Now we'll talk about one where the value of Kc is low. And this reaction here, nitrogen gas plus oxygen gas, gives you 2 moles of nitrogen monoxide. At equilibrium, you'll have a very small amount of product made. You'll have a higher amount of reactants still present. So the fact that you have a high amount of reactants present gives you a value that's going to be very low for Kc. Alright, there are going to be a few reactions that have a Kc value that's going to be close to 1, but that usually means that they're concentrations of reactants and products are going to be very close to equal to one another. The value for Kc is approximately 1. The concentrations of reactants and products will be fairly close together, or fairly equal, and you'll have a moderate reaction. If you have a value for Kc that is small, you'll get mostly reactants, and you have a very little reaction take place. And if you have a value that's going to be large for Kc, you'll get mostly products. What you'll get is a reaction that is essentially complete, because you have very little reactants left and a whole bunch of products made. Reactions with large Kc value will have mostly products, and reactions that have a small Kc value will have mostly reactant. Here's some examples of reactions and their Kc values, and whether or not you'll get more products versus reactants. So for this reaction here, fairly large value, 2 times 10 to the 11th power, so it's going to be mostly products. This reaction, another high value, 1.1 times 10 to the 7. High values, it's going to be mostly products. And the last two examples here, fairly smaller values, 1.2 times 10 to the negative 2, which is equal to 0.012. That's a small number, so you'll have mostly reactants in that reaction. And then 2 times 10 to the negative 9, that's an even smaller value, so you'll have mostly reactants for here also. Small value, reactants. If you have high Kc value, you'll get mostly products. Alright, now we'll move on to what's called Le Chatelier's principle. When the conditions of a reaction at equilibrium are changed, the forward and reverse reactions are no longer equal, because there's been a change added to that reaction. So Le Chatelier's principle states that when a stress is placed on a reaction at equilibrium, the system has to respond by changing the rate of either the forward or the reverse reaction in a way to relieve that stress. And here's what I mean by that. Let's say you have 2 tanks of water. You're at an equal level, so these are at equilibrium. Let's say that you add water to tank A, so you are changing the system. It's not at equilibrium anymore. There's a stress added here. So what that does is, in order to get back to an equilibrium, this reaction will be forced this way in order to relieve that stress. So now when the water levels get back at the same level, they're now at equilibrium again. But this change, by adding water to tank A, increases the rate of the forward reaction. So this is Le Chatelier's principle, adjusting the rate of either the forward or reverse reaction to negate the addition of the stress to that system. And here's some examples of Le Chatelier's principle with real equations. So going back to our original reaction we've talked about for this chapter, hydrogen gas plus iodine gas gives you 2 moles of HI. If you add reactants to this reaction at equilibrium, that will drive this rate of reaction toward the products. Same thing with the water tanks. You're adding more reactants here, so more products will have to be produced in order to balance out that stress that's added. So if you add any reactant, if you add more hydrogen here, that will force the reaction rate toward the products. If you add more iodine gas, that will force this rate of reaction toward the products. The forward reaction gets increased, driving the reaction toward the product. This graphic is just an illustration of that last equation, nitrogen plus iodine gas to HI. Now what happens if you remove a reactant? So let's say you take away hydrogen here. If this is at equilibrium and you take either one of these away, that's going to drive the rate of reaction in reverse toward the reactant, because you are removing a part to keep this balanced. If all this is at equilibrium and it's balanced, if you take one of these parts of it away, in order to neutralize that effect of taking away a reactant, this reaction, the reverse reaction, needs to increase. So removing a reactant will drive the reaction toward the reactants. Alright, what happens if you add product to this equilibrium reaction? If you add product here, that's going to drive the reaction toward the reactants, because you're adding a stress to the system here. In order to negate that, more reactants have to be made to balance it out. So it will drive it this way. What happens if you remove a product? Again, if these are at an equilibrium amount, if you remove some of this product, the rate of reaction will shift toward the product, because more product has to be made to balance out that negative stress, that loss of the product. So if you remove products, the rate of reaction will increase toward the product to make sure that more is made. Alright, now we'll talk about the effect of a catalyst on equilibrium. Now, catalysts will speed up the reaction by lowering the activation energy. So this will increase the rate of the forward and reverse reactions. So by increasing this rate, the time it takes to reach equilibrium is shorter, but the same ratios of the reactants and products are still there. So the catalyst will increase the rate of the reaction and it will lower the activation energy, but it does not change the equilibrium mixture of products versus reactants. Alright, now we'll talk about how the volume of a gas can impact the equilibrium reactions. And it's important to remember that when we're talking about increasing or decreasing volume, these kinds of reactions, we're only talking about gases. Alright, so if you change a volume of a gas in a mixture, that will change the concentration of those gases, either making it go up or making it go down. So for our first example, carbon monoxide plus oxygen will give you carbon dioxide. This is a reversible reaction. Let's say that we decrease the volume of the gas. When you decrease the volume of the gas, that'll make the concentration go up, and the overall system will shift in the direction of the smaller number of moles. So what you're looking for here is you're counting the number of moles on either side of the reaction. So for here, 2, and that's understood 1. So this side of the reaction has 3 moles. This side only has 2 moles. So when I say that the system is shifting toward the direction of the smaller number of moles, this reaction, if you were to decrease the volume of the gas, will be shifted toward the product, carbon dioxide, as a way to compensate. Again, we're only talking about gases. Carbon monoxide gas, oxygen gas, carbon dioxide gas. Sometimes you may get questions like this where some of the reactants or some of the products are liquid or solid or aqueous, and you cannot count those moles when you are trying to determine what way the reaction will be driven, either forward or backward. But for here, so for this reaction, there are 3 moles on this side of the reaction, 2 plus the 1, and only 2 on this side. So if you decrease the volume of the gas as equilibrium reaction, you will cause the concentration to go up and therefore drive the reaction toward the side with the smaller number of moles. In this case, it would be toward the product, carbon dioxide. Now for the opposite of that, if you increase the volume of gases at an equilibrium reaction like this, you will decrease the concentration of the overall gases. So therefore, the system will shift toward the direction of the larger number of moles to compensate. Still have the same reaction, 2 and 1, so 3 moles over here and 2 over here. So if you increase volume, you will cause the concentration to go down, and therefore it will be shifted toward the direction of the larger number of moles, which would be over here toward the reactant. Alright, now we'll talk about how temperature changes can impact equilibrium reactions. First, we'll talk about decreasing temperature. And we'll talk about decreasing temperature in an endothermic reaction. If you decrease temperature in an endothermic reaction, the system will respond by shifting the reaction toward more heat. So the shift will go toward the reactants, increasing the heat in the system. So in this example here, nitrogen gas plus oxygen gas plus heat will give you 2 moles of nitrogen monoxide. But if you decrease temperature in an endothermic reaction, the shift will be toward these reactants, adding more heat to the system. So for the opposite of that, if you increase temperature in an endothermic reaction, this will cause the system react by shifting the reaction to remove heat. So the reactions will shift toward the products, and thereby using up more heat. Same reaction, nitrogen gas plus oxygen gas plus heat will give you 2 moles of nitrogen monoxide. If you increase temperature in an endothermic reaction, this reaction will be shifted toward the products, using up more heat. Those two were endothermic reactions. Now we'll talk about exothermic reactions. Let's say that you are decreasing the temperature in an exothermic reaction. The system will respond by shifting the reaction toward more heat. So the reaction will be toward the products, increasing the heat used in the system. So for this reaction here, SO2 plus oxygen will give you SO3 gas plus heat. So if you decrease the temperature in this exothermic reaction, the reactions will be shifted toward and driven toward the products, increasing the heat. And the opposite of that, if you increase temperature in an exothermic reaction, the system will respond by shifting toward the reactants, thereby removing more heat. So same reaction, SO2 gas plus oxygen gas, SO3 gas plus heat. If you increase the temperature of this exothermic reaction, these reactions will be driven toward the reactants, thereby removing heat.
Thank you for watching our newest video on our crash course in chemistry. We'll have new videos in this lecture series every Monday and every Friday of each week. So stay tuned for our next video in a few days. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted each week.